Welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and I'm your lecturer and guide for this particular topic. Today we're covering kinematic variables and notation. So in the previous chapter, we talked a little bit about the units international, the standard units that we use. We use mass, kilograms, speed, meters per second, distance, of course, is in meters, time is in seconds. But let's look carefully at this speed, because as you can see here, speed we want to define as a scalar, which is just magnitude. We're not talking about direction with that, just talking about a magnitude. I'm going 30 meters per second down the road. I'm going 50 meters per second when the cop pulls me over. He doesn't care what direction I'm going, east, west, north, or south. He just cares how fast I'm going, the speed I'm going. Velocity would be the same units, meters per second. But instead of using meters in terms of distance, we talk about displacement. Displacement. Might be better to just give you an example here. Let me give you a little bit of an example. If I'm starting at this point, that's my x initial. From here to here, let's say I end up here, that's my x final. This distance would be my displacement Now I could also get to that same displacement by going this direction and then up here. Let's say I do 20 meters in this direction and 30 meters in this direction. We're going to use these same variables. Some books use S for that, but we're going to use X, whether I'm talking about in 2 dimensions, X and Y, or even the 3rd dimension with Z. Velocity being the change in X over the change in time. So this is my displacement here. We'll talk a little bit about the geometry and trig in the next topic. This is a distance, and this is also a distance if I'm not talking about the angle. Again, a scalar in terms of speed and velocity. Speed is a scalar, just talks about a magnitude, where velocity is a vector, magnitude and direction. Now we also have acceleration, which is a change in velocity for a particular period of time. We can look at average speed and average velocity. Again, the difference between them is both of them are divided by the total time for that particular traveling, whether it be displacement or distance. But let's look at something a little more complex. Let me draw out something else here. Suppose I'm talking about a distance with time. Because we can have a non-standardized velocity, a non-uniform velocity, or a non-uniform acceleration. Say x equals t to the third minus t squared minus 3. I don't know, that looks probably something like this. Okay? So we see this line is defined here. Okay? Now, we know velocity is equal to change in distance or change in displacement for a particular time. Well, we can also write that in notation as dx over dt. To get the instantaneous velocity, I would take the first derivative of that equation. Velocity is equal to the first derivative of that equation, which would be 3t squared minus 2t. And then we can ask the question, at any time, let's say t equals 1 second, velocity is equal to what? Well, what is velocity? At t equal 1 second, velocity is 3 minus 2, 1 meters per second. Okay? At t equal 1 second, the position is what? 1 minus 1, right? 0 minus 3 minus 3 meters. So I can look at this equation and at a particular time get the position from the position equation, take the first derivative to get the velocity equation, and I'm going to take this one step further because there is something called instantaneous acceleration, which would be change in velocity for a particular time. Therefore, acceleration at a given time for this particular equation here, this is the first derivative. I would take another derivative of this. It's 6t minus 2. So at 1 second, what do we have for in terms of acceleration? 6 minus 2, 4 meters per second squared. So if given a non-uniform curve, a non-uniform velocity, as defined by a particular equation, taking the first derivative gives me velocity, taking the second derivative gives me acceleration, and for a given time, I can get a position, a velocity, and an acceleration. Now, this is just more of a statement that acceleration is a change in velocity for a particular time that it takes to make that change. And we just went over how for instantaneous velocity you would have a change and you could also have a change in velocity for a particular period of time being instantaneous acceleration. So in describing the motion of kinematics, we've covered how we can look at velocity and how we can look at acceleration. Time, displacement, velocity, and acceleration are the only variables we really need for kinematics. In addition, of course, as I just showed you on the whiteboard, we can also calculate instantaneous. Two separate topics in a sense. We have the way through calculus to find an instantaneous velocity or instantaneous acceleration by taking the first and second derivatives. And then we have kinematics, which uses velocity and acceleration, and of course time and distance. So that's the notation that we're going to use in this course. Now, let me just give you a brief example of how that notation would come in to these problems. One of the things you need to get in this course is that we're going to have English language problems, and we're going to be translating them into the mathematics and choosing the proper equation to solve that. That's pretty much what we're dealing with in general physics. So let's say we have an airplane. You know, the airplane is coming in for a landing. Okay, and it's going 100 meters per second. And it comes to a stop in 5 seconds. Okay? Well, in our notation, we know our velocity initial. What is our velocity initial? 100 meters per second. Velocity final, we say we came to a stop, 0 meters per second. And we have the time change. Well, in this case, the change in time is just merely 5 seconds. So, the acceleration, which is velocity final minus velocity initial over change in time, leads us to velocity final 0 minus 100 over 5. Our acceleration is a negative 20 meters per second squared. So this type of notation you'll be seeing in our kinematics, and gives you an idea of most of the books use this type of notation where they do a subscript of I for initial, subscript of F for final. And as you can see here, we calculated the acceleration. If we go back to that previous example where I may have walked this distance over here, then walked up here, this is my initial position, this is my final position, and as I said before, this is the displacement in between. Okay? So how long I took to make that trek, okay, would give me my average velocity, x final minus x initial over change in time. Now, as I said, I'm using x here, of course, but some of the books use s in terms of you know, what displacement is. I use X for any dimension, whether it be X, Y, or Z. And just to make sure that you're aware that kinematics in one dimension, second dimension, we're going to cover it in a separate chapter. But we're talking about X being a displacement. And it can be in any direction. This could be X and this could be Y. And we can do the kinematic equations that we're going to see later on in terms of X, Y, and it could be in Z. We can also talk about our notation in terms of I wrote these backwards, forgive me. This is Y, this is X. And this is called unit notation. J, and in the Z direction we would use K, and that's called unit notation. So if I have a position I can define in its 3-coordinate system as let me just write that down. Hold on. 4I minus 2J plus 3K would be defining, my position. Okay? Just think of these as units of 1 that sort of define the direction we go in. This is called unit notation. We could also write it, and you're probably more familiar with this notation in geometry. So I wanted to introduce the unit notation as well. So there you have it. Again, there is a specific assessment for this particular topic, and good luck.